phase diagrams. Now, in our last section, we talked about the heating curve of water and the 5 segments of that, 2 plateaus and 3 areas of increasing temperature. Phase diagram is probably something you're a little bit more familiar with. This is something that we have talked about more in the intro class. Which would you predict should be larger for a given substance? Delta H vaporization or delta H fusion? Well, what are these terms? Delta H vaporization is the energy needed per mole to vaporize a particular substance, and delta H fusion is the energy needed to melt a particular substance. So, which would have more energy? Which one will take more energy to do? Let's see if they tell us. Oh, and they say explain why. And they just say delta H vaporization. It's pretty obvious that it's going to take more energy to go from a liquid to a gas. More energy is going to be needed because those molecules need to be significantly further apart than they do in a situation with fusion where you're going from a solid to a liquid. Think about an ice cube and think about that melted ice cube. Sure, the molecules in the melted ice cube are more freely flowing, but you notice the proximity to the neighboring water molecule isn't that different. Whereas when you become a gas, that water, same volume of water, becomes a gas. There is a significant difference in the location of those molecules. They are much further apart, and you're really going to have to add a lot of energy to separate them. A convenient way of representing the phases of a substance as a function of temperature and pressure is by noting these particular spots on a graph: the triple point, the critical point, the phase equilibrium lines, and you can notice here that's what is shown here. Phase diagram for carbon dioxide. In a phase change diagram, you have the 3 phases of matter: solid, liquid, and gas. The solid is always to the left of the Y shape. You notice the liquid shape here. The liquid shape here is always in the middle of the Y, and the gas is always to the far right. Triple point is where a solid, a liquid, and a gas can all exist at the same temperature and pressure. You can read that off here. Here, the triple point is a pressure of 5.1 atmospheres and a temperature of negative 56.6 degrees Celsius. And this is for carbon dioxide. The critical point is, you notice, after that point, you can't liquefy it anymore at that particular temperature. And here's a phase diagram for water. You notice it looks quite different than the carbon dioxide one. Remember, water's a bit of an unusual substance. You notice the solid-liquid line actually goes backwards. Usually, I'm going to flip back to the previous diagram. Notice how in carbon dioxide you have this kind of Y shape right here, and it's kind of, if you will, bent to the right. However, with the phase diagram for water, it's somewhat bent to the left, more open, greater liquid section. So we can tell the 3 phases of matter, and at standard pressure we'd simply read across, figuring out whether the substance was a solid, a liquid, or a gas, and when it hits one of those lines, like in this case the solid-liquid line, we can say that that's the exact, like in this case, this is the pressure at which ice changes to water, and that temperature, so we can read it off. So if that was standard pressure, we would assume that the temperature would be 0 degrees, because that's when water becomes, solid water becomes liquid water. As intermolecular forces increase, what happens to each of the following? What happens to the boiling point? Well, we know as the boiling point increases, as the intermolecular force increases, boiling point increases. It takes more energy to break apart neighboring molecules. Viscosity, or thickness. Things that have high intermolecular force also have high viscosity. You might not think so. I'm going to go back to that in a minute. and surface tension. These two things are related. Things that are viscous, those molecules can't slide past each other well, and therefore they have a very high surface tension. Water has a high surface tension and a relatively high viscosity. You might not think water is being very viscous as compared to, let's say, maple syrup, but maple syrup is a much bigger molecule. It's a sugar molecule. Water has only 3 atoms, and water has a pretty high viscosity. Think about a nail polish remover or astringent or some, rubbing alcohol. These kinds of materials are very, you could say, watery and thin. In fact, when they hit our skin, they're often very cold to the touch because they become a vapor so very quickly. That's because they have a weak intermolecular force. So, as intermolecular force increases, all of these things so far are increasing. The enthalpy of fusion. How much energy does it take to break apart the solid to become a liquid? Again, intermolecular force increases, so does enthalpy of fusion. How about the freezing point? It may or may not have too much effect, but it may have an effect. And then the vapor pressure. As the intermolecular force increases, the vapor pressure also increases because, actually the vapor pressure decreases because it takes more energy actually to become a vapor, and therefore a higher temperature, so the vapor pressure decreases. I was thinking of the vapor pressure, the atmospheric pressure, but indeed the vapor pressure decreases as intermolecular force increases because it doesn't vaporize easily. And so you should be familiar with the phase change diagrams and being able to interpret and read them. They have some nice examples in your textbook. You can look those over, and hopefully you can be reminded of the kinds of questions that we did back in Intro Chem. And then finally, intermolecular force related to heat of vaporization. Heat of vaporization, how much energy does it take to vaporize something from a liquid to a gas? It's going to take a lot of heat of vaporization the higher the intermolecular force, because you're going to have to overcome those intermolecular forces for the substance to vaporize.